All right, so this week we're going to be taking a look at one section, okay, just section 2.4, and it is on graphing. So we've studied a little bit about sine, cosine, tangent, all the different trig functions. This week we're only going to look at two of them, sine and cosine, just those two. And what we're going to do is look at what they look like. All right, so before we can transform them, okay, and we've done transformations before, like shifting left and right, stretching up and down, things like that. Before we do the transformations, I want to show you what the original graphs look like. Okay, does anybody know what sine or cosine look like if you graph them? Yep.
Just a wave.
Yeah, it looks like a wave. Yep, exactly. So let's just take a look at what it looks like. So it's a wave. That's a graph of sine. And you'll notice that it does repeat itself, okay, over and over. So basically, once you know what a certain section of it looks like, you can copy and paste that, and that's what the whole graph looks like. And if you graph cosine, it's going to look very similar. What's the difference between the two?
Shifts back one.
Yeah, it's like it's just shifted a little bit. If you took the blue one and moved it a little bit to the left, or you took the red one and moved it to the right, then they'd look identical. Okay, so sine and cosine look very, very similar. The graphs we're not going to look at, tangent. Okay, this is not one we do. Okay, big difference with that one, it's not connected. It does have a repeating pattern, just like sine and cosine, but it's not a wave. Okay, so we're gonna focus on the red and the blue one. So let me get rid of these other two. And because the wave repeats itself over and over, we're only going to draw one section of it when we graph it. And then the understanding is if you can draw one section, you could kind of copy, paste it, and draw more sections. So when you have a graph that repeats itself over and over like that, that is called periodic. Okay, it's the only function we've studied so far this year that is periodic. No other graph we've done repeats itself over and over. Okay, lines don't do that, parabolas don't, square roots, logarithms, all those other ones we've studied, they don't do that. So what makes something periodic is that the y values repeat themselves. Now you have to travel a certain distance before you notice that it repeats. And I'm going to show you what I mean in a second. Yes?
Can we scroll back up? Thank you.
Yep. All right, so let me put, I'm going to take this graph, and you know what, let me go like this. Let's take this like that. Like that. Let's put that here. So it says that the y values repeat themselves over a given set of x values. Okay, so let me show you on that graph what I mean. Well, let's start right there. Okay, what's the y value of that red dot that I just put? 0. Yep. And then for this graph, it starts to go up, and it hits its highest value right there. What do you think that highest value is? 1. Yep, that's the highest it ever hits. So it goes up, comes back down to 0, then hits its lowest value at -1, and then comes back up. So 0, 1, 0, -1, 0. That pattern of numbers is what's going to repeat over and over. 0, 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1, 0. Those values keep repeating. And they repeat over a given set. The set that they repeat over is from here to here. That what I just drew in purple, that's the amount of distance that you have to travel before you notice the graph starting to repeat. Okay. If you don't travel just move that so you can see it easier. If you don't travel as far as that purple line, you won't notice it repeating yet because it hasn't started over.
So would you say each possible y value repeats like infinitely?
Yeah, it repeats forever. Yep, the more that I zoom out, the more you'll just see that wave continuing. Yep, never stops. So the length of that line that I drew in purple, that is called the period of the graph. It's the amount of horizontal distance that you have to travel before the graph repeats. And then again, that's called the period of the graph. For sine and cosine, there is a standard length to that. This length is 2 pi units. From there to there. That's the amount of distance you have to travel before it repeats. Okay, and that's in radians. What's 2 pi in degrees? Uh, 90, that's pi over 2.
180.
180, that's pi.
360?
That's 360. Yep. So in degrees, you have to travel 360 units on the x-axis before the wave repeats. In radians, you have to travel 2 pi units on the x-axis before the wave repeats. So if I wanted to see just one section, that section I drew in red, if I'm in degrees, I can start at 0, which is the first red dot. I can stop at 360, which is the last red dot. And all you're going to see on the screen now is that one section that I traced in red. So I've kind of zoomed into just that piece. Because I zoomed in, it distorts it a little bit. But it is still going up to 1 and down to -1. I'm going to do the same thing in radians. Now, one thing is, if you graph on the calculator and you set your window, and it's all set for degrees, and then you change the mode, it won't look right at all. Okay, when you change it between radians and degrees, you have to go back in and change your window. Okay, if you don't, you get a picture that looks like that, which is not what you want. So I'm in radians, and I want to just look at that section in red. So the first red dot is at 0, and the last red dot is at 2 pi. Now it should look right. Okay, any question on that idea that if you changed between radians and degrees, you've got to change your window? Now, what if I wanted to see 2 periods? That's 1. What could I adjust my window to so I could see 2 full periods? What do you think I'd have to change?
Your X scale?
My X, what?
Your X scale?
So the X scale just controls how often you see a tick mark on the screen.
Oh, your
That's
X
more of
max.
just a visual thing.
Your X max, sorry.
Yes, I'd have to change my X max.
Double it.
Double it. So if 2 pi gives me 1 cycle, what would it be for 2 cycles? 4 pi. So if I set that at 4 pi, now you're going to see the first cycle. That's the end. Now it's doing the second cycle. That's the end. That's 2 full cycles, okay, or 2 full periods. We'll use the period. We'll use the term period and cycle kind of synonyms interchangeably. I think I already got at that idea. So if you continue to graph after 2 pi, okay, if you go beyond this first section, you're just going to see this first section in red repeat itself. That's all that's going to happen. We saw that on the calculator. When I went beyond 2 pi and I set it to 4 pi, That's exactly what it did. It just repeated the section you already saw. And it repeats to the left as well. So if you wanted to set this at negative 2 pi, now you're looking at 1 cycle to the left, and now you're looking at 2 cycles to the right of the y-axis. So that graph right there, that is 3 full cycles of the sine function. And I've already been using that word with you, cycle. Okay, 1 period of the graph, 1 cycle of the graph, same thing. Sometimes you see the word cycle used in other trades or other areas like sound. If you measure the frequency of a sound, it's measured in cycles per second. That's how you measure the frequency, how high or low pitch a sound is. And cycles per second is known as hertz. There's hertz, kilohertz, megahertz. Those all measure frequencies. Another thing that cycles per second is used for is AC electricity. So if you measure the kind of electricity in your house, not your car, that's DC, but in your house, it runs at 60 cycles per second. Right? That's in the US, 60 cycles per second, and that's known as 60 hertz. Right? So a hertz is a measurement of how fast the electricity alternates per second. Yeah.
If a period is a cycle and cycles per second equals hertz, is that why, like, when you see like a visual representation of music, it kind of has like that wavy line?
Yeah. So if we looked at what something sounds like on an oscilloscope, we can convert sound into a picture. And if you make a very simple sound, like whistling, you would see a nice wave. So hold on 1 second, I can show you. Okay, so what you're looking at there, that's a picture of my voice. So the higher and lower it goes, that's loudness, right? So if I talk quieter, you won't see the wave hit the top and the bottom. But if I start to talk louder, then you see it go higher and lower. So that's called the amplitude. And then it doesn't really look like a wave because my voice is not a simple sound. Right? What you're hearing right now is thousands of different frequencies that all kind of come together to make my voice. So right now you're looking at a picture of my entire voice, but I can also separate that into different frequencies. So if you look at this chart, it's showing all the different frequencies that make up my voice. So there's not really that many high pitch frequencies, but a lot of the lower frequencies, maybe 0 to 4,000 hertz, that's the frequencies that make up my voice. Now, if I whistle, you'll see a spike just at a certain frequency. You'll see a very, very simple looking graph. So let's see if I can do that. So you saw that spike right there, and that was just that frequency. Very, very simple sound. And the graph will also look a lot simpler when I whistle. So as I got louder, you see the wave get taller. And it also looked more like a wave. It wasn't perfect because I couldn't keep it exactly perfect volume. But yeah, that's basically a device that converts sound into a picture. It's called an oscilloscope. Yeah. All right. So period cycles per second. All right, so I kind of showed you this a little bit, but when you are graphing one of these functions, you need about 5 different points to make a good sketch. Okay? We do the one at the beginning, the end, the middle, the high, and the low. Those 5 points will give you a pretty good sketch of one cycle. Okay, and I call those like the 5 key points or the 5 important coordinates, whatever you want to call them. So let's think in degrees for a second, how far apart all these points would be. So if you go from, it's going to be easier to think in degrees for a minute. If you start at 0 and you end at 360, Okay, that's going to give you first section, second section, third section, and fourth section. So going from 0 to 360 and putting those 5 dots in gives you 4 different sections. So how far apart do you think each one of these dots is if there's 4 sections over 360 degrees? Yeah?
90.
Yeah, they're all 90 apart in degrees. We're going to do some work in radians, but yes. This is at 0 degrees, 90 degrees, 180, 270, 360. Right. And let me label those, except I'm going to do it in radians. So this is 0. This right here would be pi over 2. That's pi. 3 pi over 2. And 2 pi. Those are the x values of those 5 green dots. The y values, 0, 1, 0, -1, 0. So we're going to write those coordinates down because anytime we do a transformation, we have to know where the graph starts. Well, that's where it starts. And then we can adjust them to figure out how it's going to move. So if we don't have these tables right, then every graph that we do based on these tables will be wrong. So it's very important we have these tables correct. There's one table for sine, and then there's a different one for cosine, because cosine starts at a little bit different spot. Okay. So what would be the coordinate of that first point that I just circled?
0,
0,
0.
0. Yep. That's the very first point that we're going to graph in sine. Is it the first point in the graph in general? No, there is no first point in the graph, because the graph goes on forever left and right. Right? It's just the first point we're going to graph, 0, 0. Okay. How about the coordinate of this next point?
1 over 2.
So how far to the right do you go?
Pi over 2.
And how far up?
1.
1. So what would that coordinate be?
1, 1.
Well, it's going to be the numbers that you just said.
Oh, pi over 2, 1.
Pi over 2, comma, 1. Yes. That's the second point in the graph of sine. Could you do more points? Yeah, you could do more, but the 5 that I showed you is really all you need. That's enough detail. How about this one? What's that third point going to be?
Pi 0.
Pi 0. Yep. So that is the halfway point, okay, pi 0. Okay, the next point, this is 3/4 of the way through the graph. What would be the coordinate of that?
3 pi over 2 is -1.
3 pi over 2, -1. And now we need the last point, which gives us the very end of the cycle. And that point is right there. And where would that one be?
2 pi 0.
2 pi back at 0. So this point is all the way back now where we started, and it's going to begin the next cycle of the graph. 2 pi 0. All right, so those are what we call the 5 key points, 5 important coordinates for sine. Cosine is going to have the same x values. We don't want to mess that up. Okay, it's very important that when we're graphing, we always have x values that are equally spaced. And these are 0, 90, 180, 270, 360. But the y values are a little bit different with cosine. Let's put the graph of cosine. And let me set the window to be 1 cycle. And I can put the tick marks in there. There's no tick marks. I didn't set them. But if you want to see them where they're supposed to be, Let's go to window, and let's put a tick mark every pi over 2. So there they are. All right. So first point is, let's take this right there. What's the y value for your first point? 1. Yep. And then the second point, this is pi over 2. What's the y value there?
0.
0. So we get that. The third point is at -1. And then the fourth point,
0.
we're at 0. Bless you. And the fifth point is at 1. And now we're back at the point that is going to start the next cycle. Okay. So that's what, when we graph cosine, that's what it's going to look like. It's still a wave. It's just, it's been shifted a little bit. So instead of looking like the graph of sine, it's more the middle part of the wave. Think of it as like this section here. But it's still a wave. Okay, none of the graphs that we sketched this week should be straight lines or anything that has like a sharp turn. Everything is curved, nice and smooth. Okay. All right, so any questions on those two tables? Let's move this out of the way in case you need to copy that. All right, so that's going to be our starting point for every graph we do. So the next thing we have to do is figure out how the points in that table are going to change. Let's say that I did something like this. Let's take that graph. Let's do cosine x plus 2. What did the plus 2 do to the original graph?
Shift it up 2.
It shifted it up 2. Now, when you shift something up or down, which column of values is affected? The x's or the y's?
The y's.
The y's. So all we would have to do is take the original values. We wouldn't touch the x's if we shift up. All we'd have to do is add 2 to all these y values, and that would give us our new table. What about if I did, let's try another one. Let's put instead of putting a 2 at the end, let's put a times 2 at the beginning. So let's look at what, actually any guess before I show you what the times 2 is going to do? Yep.
Increase like the height of the peaks.
Yeah, it's going to stretch it taller. So if you look at that graph, it didn't move left and right. It didn't move up and down. It stretched up and down. So now instead of the highest being 1 and the lowest being -1, the highest is 2 and the lowest is at -2. So what that would do is it would double all the y values in the table. So the x's would stay the same, and these would become 2, 0, -2, 0, and 2. So that's the idea of pretty much every graph that we do. Okay. I'm going to use the original table. One column is going to stay the same, and the other column will change. So in the example that I did, shifting it up 2, the y values changed, the x values did not. The reason one column will stay the same and one column will change is because we're never going to do multiple transformations at the same time. If I gave you a problem that, say, shifted the graph left 2 units and up 5 units, then everything would change. Okay? Because moving it left would change the x's, moving it up would change the y's. We're never going to do one that has more than one transformation per problem. Okay? All right, so that's pretty much kind of the background on sine and cosine. Everything we do now is going to focus on how do you graph one specific transformation. The transformation today is a phase shift. So we've done phase shifts before, we just never called it a phase shift. But a phase shift is just when you move the graph left or right. And I can show you an example of what a phase shift sounds like, because I can tie a lot of what we're learning in this week with sound frequencies, kind of like I did with the oscilloscope. But I'll show you what a phase shift sounds like, and I'll show you what it looks like. All right, so this program is going to show you what a phase shift looks like. So what I can do, I might have to do it over here, but notice if you look at the wave right now, that red wave is sliding to the left. Eventually, if I slide it enough to the left, it lines back up with where it started. And notice the amount, I don't know if you can read it right there, but the amount that I have to slide it so that it lines up exactly back where it started is 360 degrees or one full cycle. So if I were to play that sound, or I were to play this sound, putting it back, you wouldn't hear any difference between the two, because it was shifted one full cycle and the picture lined back up where it started. But that's what a phase shift looks like. So it's when the graph is translated left or right. So if I play, hold on a second, let me, it's kind of loud. Okay, so that's the sound that you're hearing. That's 1,000 hertz. Okay, that's a cycle. That means the sound is cycling 1,000 times per second, and that 1,000 times per second translates into what you hear. Right? It's not super high pitched sound. Let me just turn it down a little bit. Now what I'm going to do is I'm going to slide the phase to the right, and I'll let you kind of hear it as it's moving. Okay, so what did you hear as it moved?
Go quieter.
It got quieter. Now, there's two speakers that are playing there, that front speaker. There's a left and a right. If we could somehow take that speaker apart, break it into two pieces, and go put one speaker in one room and one speaker in the other room, you wouldn't have heard any difference at all. You wouldn't have heard any change, because there was no change in the volume. At no point did that wave, basically a change in the volume would have looked like this. You would have saw the wave start to flatten out. That didn't happen. Okay, the wave did not flatten out. What you were hearing was the left and the right speaker being played out of phase, and what happens when two things are out of phase is it's almost like they fight each other, like kind of like a tug of war between the two sounds. One sound is trying to do one thing, the other sound is trying to do the opposite of that thing. So the idea is the sounds actually interfere with each other and they cancel out. Right? Kind of like different waves interacting like on a lake. Like if you were in one part of a lake and you threw a rock and somebody was in another part, those waves are, it's going to make circular waves that come out. As those waves start to move and they hit each other, at one point, there's not going to be a wave at all when the two waves pass through each other. They're going to cancel each other out. Yeah.
Is that how noise canceling headphones work?
Yep, that's the same idea. Yeah, how noise canceling headphones can work. Yeah. So you heard it getting quieter, but it wasn't really getting quieter. And if I could take that speaker and put it through the wall, so the left was in one room and the right was in the other, you'd hear nothing at all. There would have been no change. All right. So for me, the quietest I heard it was right about there. That was the quietest. Was that quiet for other people? And that's quiet? Yeah. So that's where it's kind of canceling out the sound. I almost don't even hear it, just a little. Now I hear it again. So that's basically what a phase shift sounds like. Okay. What does it look like as an equation? The way that a phase shift looks when you write an equation is when you add or subtract a number inside the parentheses. Now you saw me do a +2 before, and it shifted it up 2. I did the +2 over here. I didn't do it inside the parentheses. If I had, you would have saw it move left and right 2 units instead of up and down 2 units. All right, so now when you do a phase shift, that's moving it left and right. You can move it left and right any amount you want. And you saw that in this program. I shifted it every single degree between 0 and 360. I just used the slider, so you heard it every single phase shift between 0 and 360. It's not very common to shift the graph by like 13 degrees or 26 degrees, right? They usually use certain numbers. So when we start dealing with a phase shift, you're either going to see a shift amount of 90, which is pi over 2, 180, which is pi, or 45 degrees, which is pi over 4. Those are the most common amounts to shift by: 45, 90, and 180. Again, could you shift by any other amount? Absolutely. If you want to shift it by 12.4 degrees, you could do that. It's just not a very common problem to look at. All right. So there's 2 different ways when you are shifting that it can move horizontally. It can move left or it can move right. Let's try something and see if we can figure out. Okay, here's cosine. And now I'm going to do cosine of x plus pi over 4. That's a 45-degree phase shift. My question is, do you think the graph is going to move left pi over 4 units or right pi over 4 units?
Right.
You think it's going to move right? All right, let's try it. Okay, so here's the original. If it moves right, then the red one would be a little bit to the right of it. It moved left. All right, so now if you look, the red one is to the left of the blue one. So it took that blue one and moved it left a little bit. So the rule is when you see addition inside the parentheses, addition will move it left. Subtraction would move it right. So those are the 2 rules that describe the directions that something can shift. X minus a value will shift it to the right. X plus a value will shift it to the left. And for a lot of people, that's the opposite of what you would think. Because usually when you think of like add, like plus horizontally, you think plus would go right, because that's the direction of positive numbers. Well, it's just not the way it works. So minus is right, plus is left. So the key thing we have to remember about phase shift is it is backwards. It's not what you would expect. All right, so the last thing we have to do before we can graph it is we have to figure out what column in our table is going to change and which one stays the same. When you move left or right, what part of a coordinate does that affect?
The x.
It affects the x. So the y's are not going to change. So when you are doing a phase shift or horizontal shift, you're going to copy the y's down from the original table. And remember, you have 2 tables. One for sine, one for cosine. So make sure you copy them down from the correct table. Just look at your problem. If you're doing a sine problem, use the sine table. All right, well, if the y's are going to stay the same, then all of the x's are going to change. But remember, everything is backwards. So when you see minus, the graph has to go to the right, plus, it has to go to the left. Okay, so the way you're going to find the new x's, first thing you're going to do is look at your problem. Our problem is x minus pi over 2. Minus pi over 2 should move the graph which way? Right. It's going to move it to the right. When things move to the right, the x values, what happens to the x values as you move right?
They go up.
They go up. They get bigger. The only way something can get bigger is if you add to it. That's how you make it bigger. So you look at what you have inside your parentheses, and you do the opposite of what I just circled to all of your x values. So because I want that graph to move to the right, I need to make all my x values bigger. They all have to get bigger. How much bigger? Pi over 2 bigger. So I'm going to add pi over 2 to all the x values. So for each question, there's going to be two parts to it. The first part is going to be to make a new table, and the second part is going to be to make a graph. Most of the points are the new table. Okay, the way I graded on the test this week, you'll have a table in pair assessment. There'll be 10 blanks, and you'll click in each spot and type in the number. You get 1 point for every number you get right in the table. So that means the table is going to be worth 10 points. 5 for the x's and 5 points for the y's. Once you get the correct table to draw the sketch, that'll be worth 2 points. So a problem like this would be 12 points on the test. 10 for the table, 2 for the picture. All right, so let's see if we can make our new table. Okay. So first, it is a phase shift. We know that because it fits the pattern that I described earlier. Adding and subtracting inside the parentheses. And what column is going to stay the same when we do a phase shift?
X.
Y.
On the side, Y.
Y is going to stay the same. We're doing a sine problem. So what are going to be my y values when I make my final table?
Same thing as
Right, I just copied down the original table from the notes a couple slides ago. So we can keep the y's the same. 0, 1, 0, -1, 0. All my final answers are going to be in that box. Off to the side, I'm going to put the original x's. 0, pi over 2, pi, 3 pi over 2, and 2 pi. These all need to be modified. Am I going to add or subtract to all of them? Yep, I'm going to add. And how much am I going to add to each one of them? Pi over 2. I'm doing the opposite of what I have in parentheses to each of the original x values. Now I have to figure out what that comes out to. And then we'll put all our answers in that box. Okay, first one. What's 0 plus pi over 2? Pi over 2. What's pi over 2 plus pi over 2? Pi, because they already have a common denominator. That's 2 pi over 2, which reduces to pi. Okay, the next one. pi plus pi over 2. Do they have the same denominator right now?
No.
No. What's the common denominator between pi over 1 and pi over 2? 2. So how would you make the fraction on the left have a denominator of 2? Do what? Times it by 2 in the bottom and the top. So now you've got 2 pi over 2 plus 1 pi over 2. And that gives me a total of
3 pi over 2.
3 pi over what?
2.
2. Yep. Okay. Next one already has a common denominator. Without reducing it, what's 3 pi over 2 plus 1 pi over 2? 4 pi over 2. And now what does that reduce to?
2 pi.
2 pi. Now, if you're doing this right, you should notice a pattern. And that's why I didn't reduce it right away, but I showed you what it reduced to after. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. What do you think the last one is? 5 pi over 2. And if we kept going, the next one after 5 pi over 2, 6 pi over 2, which reduces. 7 pi over 2, 8 pi over 2, 9 pi over 2. That's the pattern. Okay. When you reduce it, you won't see the pattern as easily. But if you leave everything with a denominator of 2, you will. Okay. So that is your new table. Any questions how we got those 5 points?
Does that pattern work for sine and cosine?
There's always a pattern, but sometimes it's a little bit different depending on the problem. Yeah. There is always a pattern. All right. Now, we started with these x values. They were all equally spaced. This was 0, 90, 180, 270, 360. We're just not doing degrees. If you take 5 numbers that are equally spaced and you move them all together the same amount, are they still equally spaced?
Yeah.
Yes. Yep. So when we graph this, these x values are not nice. Like this is 3.14, 2 pi is 6.28. We don't want to label our x-axis using numbers like 0, 1, 2, 3, 4, 5. We want to label our x-axis using the values from our table. Because the only rule when you're labeling tick marks is you have to use things that are equally spaced. And our values in the table are. So let's use them. So this will be 0. The first tick mark is going to be pi over 2, pi, 3 pi over 2, 2 pi, and 5 pi over 2. That's the label for each tick mark. And I wrote it down a little bit lower because I'm going to be drawing in that area right there. So if you put your labels right on the tick mark, you're going to draw through them. So I put them down below. Okay. What's the highest y value that we have in this table? 1. So we'll make this top tick mark 1. Not worried about putting a label there because my graph is going to be over here. And the lowest that we go?
-1.
-1. It's a little bit easier if you have graph paper, but we can use that. So let's graph all the points in that table on that graph. So the first point is pi over 2, 0. That is right there. The next point is pi 1. Second point. Third point, 3 pi over 2, 0. The fourth point, 2 pi. We are at -1. So right about there. And the last point, 5 pi over 2, back at 0. Now, when you connect them, remember that the curve it's a wave. So try to make it look kind of like a wave. Just like that. Okay. That is the new graph. If you want to compare it to the one we started with, that would have been here, 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 there, and there. So I'm just comparing, I'm showing you both, the new one and the original. So you can see that the new one moved to the right exactly pi over 2 units. One tick mark. Okay, and that's a phase shift. Any questions on that? And part of the reason why we only shift either pi over 4, pi over 2, or pi is because then it keeps it lined up with the tick marks. If you didn't shift those amounts, you might start ending up in the middle of tick marks, and then it gets kind of messy to draw. Okay, let's look at this one. All right. So looking at cosine x plus pi, how do we know that that one is a horizontal shift?
It's plus.
All right, plus or minus always means that it's a shift. How do you know it's not shifting up and down? It's in the parentheses, yes. It's in the parentheses, and it's adding or subtracting. That's shifting left and right. Yep. Okay, so let's make our new table. We're shifting left and right. We already agreed on that. So what values are not going to change?
Y.
The y's. So now I need my y values from the cosine table. And that is different than the sine table. What are my original y values?
1, 0, negative 1, 0, 1.
Yep. 1, 0, negative 1, 0, and 1. Okay. So we've got our table. And what are the original x values? I'm just going to put them off to the side.
0, pi over 2,
2,
pi, 3 pi over 2, and 2 pi.
2 pi. Okay, all those x values need to be adjusted. And what are we going to do to all of them?
Minus pi.
We're going to minus pi. Yep. Start with the first one. What's 0 minus pi? Negative pi. Okay, the second one, pi over 2 minus pi. We don't have a common denominator. So it's minus pi. I'm just going to put a 1 in the bottom. Common denominator between 1 and 2? 2. So you're going to double the bottom and double the top. What's 1 pi over 2? Take away 2 pi over 2. Negative pi over 2. Okay, next one already has a common denominator. What's pi minus pi?
0.
That's 0. Okay, 3 pi over 2, take away pi. That's basically the problem we just did, but just change it to 3 pi over 2. Take away 2 pi over 2. That's pi over 2. So now if you look at your pattern, yep, this is 0 pi over 2, 1 pi over 2. This is 2 pi over 2, which we normally just write as pi. And that's your table. Any questions on the table this time? Okay, this time we do need 2 values in the negatives, so we're going to start with negative pi over 2. You don't have to label the axis as 0. I mean, I know it's 0. It has to be 0. But if you want to, you can. This is pi over 2 and pi. Okay, and now graph all the points. So at negative pi, you are at 1, 0, negative 1, 0, back to 1. Now, remember, it looks kind of like a V shape, but remember, there is no V in this graph. You're basically going to draw this. So it has a curve to it. Okay, so just draw it the best you can. Like that. Okay, and which way did that graph move? Did it move left or did it move right? Yeah, it moved left. The original, I'm not going to draw it this time, but the original would have been more like that. Our graph, more like that. And did it move more or did it move less than the last problem? More. Yeah, it moved twice as much. Right. This graph moved by half pi. This graph moved by a full pi. The other way. Yes, it moved twice as much. That's an example when I played the phase shift where the two sounds almost canceled each other out. If you looked at them together on the same graph. This is one where they were starting to cancel each other out, but it wasn't quite shifted enough. You'd have to move it a little bit more like that for the sounds to completely cancel out. All right, and let's look at one more. So this is the smallest shift we've done yet. This is a shift of pi over 4. Okay, it's a shift of about 45 units if you were doing it in degrees. Okay. So the last time, which column stays the same? The y's. And what are my y values for sine?
0, 1, 0, negative 1, 0.
0, 1, 0, negative 1, 0. All right. And what were the original x's for sine?
0, pi over 2, pi. 3 pi over 2, pi.
Yep. Those aren't part of my answer. I'm putting there because I need to do some arithmetic, and it helps if I write them down. Okay. What are we going to do to all our x values?
Plus pi.
We're going to plus pi over 4. Plus pi over 4. All right, first one, that one's pretty straightforward. What's 0 plus pi over 4? Just pi over 4. Okay, next one is pi over 2 plus pi over 4. Do they have a common denominator right now? Well, right now, do they have a common denominator? No. So how do we make a common denominator? We're going to multiply. What would you multiply the top and the bottom by? 2. Times 2 times 2. So what do you get when you simplify that?
2 pi over 4.
Well, the first one is 2 pi over 4 plus 1 pi over 4.
3 pi over
It gives you a total of 3 pi over
8.
4. Yeah, when you're finding common denominator, you keep the denominator the same when you do the arithmetic.
Good.
Next one, pi plus pi over 4. What's the common denominator this time? 4. It's going to be 4 for all of them. Times the bottom by 4, top by 4. 5 pi over 4.
Just adding 2.
Yeah, the numerator just goes up by 2 each time. So the next one?
7 pi over 4.
7 pi over 4. And the last one?
9 pi over 4.
9 pi over 4. Oh, there's your table. So now look at the numbers that are in the numerator. 1, 3, 5, 7, 9. Okay. Yeah, they're all odd. Now imagine you were putting those on a number line. Forget the pi over 4 for a second. Okay. Let's say I put 0 right there. So that's 0. Then I put 1 right there, because I'm putting these numbers down. So I got 0, I got 1. Would 3 go right next to 1? No.
Skip it.
It would have to skip it. We'd have to skip it because that's how the numbering works. 2 would go there. 2's not in our table. 5 would have to skip. 7 would have to skip. And so would 9. We have to do exactly the same thing when we do it with pi over 4. Okay. If this is 0, the first one can be 1 pi over 4, but the next one is 3 pi over 4. So we're going to skip because that's 2 pi over 4, and go to the next one. That's the only thing that's a little bit tricky. You got to be careful. Because of your numbers, you have to skip when you label it. Any question on that? Okay, I'm going to need some more. Hopefully that's enough. Let's see, 3 pi over 4. We're going to skip 4 pi over 4 and go to 5. Skip 6 and go to 7. And we'll skip 8. And we'll go to 9. And that's our labels this time. Okay, so you always want to use the numbers in your X column for your labels. Then it'll make the points land right on that tick mark, and you don't have to try to figure out weird decimals. We don't do anything with decimals when we have pi in a fraction. All right, so pi over 4, we're at 0. 3 pi over 4, we're going to go 1. 5 pi over 4, you're back at 0. And then my tick marks started to not get spaced as nicely, but that's okay. And 9 pi over 4, we're back at 0. So this is a graph of sine. Sine, you always, when you graph one section, you always see that kind of S curve to it. Like that. Any question on that?
It didn't stretch, right? It's just the way the graph is.
Yeah, it didn't stretch. It's just the way that the tick marks are. Yep. The problem with always using these labels every single time, 0, pi over 2 pi, is if you've got to deal with fractions with 4 in the bottom, now you'd have to be in between tick marks. By labeling it the way I did, I avoided that problem. And that's it. So that's facius. So the homework for tonight will be a worksheet, and let me just show you where that is. So in Schoology, you'll click on Lesson 11, click on Homework. I think there's maybe 4 or 5 questions. So each graph says make sure that you make the table. Okay, so I need to see the table, and then I need to see the sketch with your axes labeled. And you can label them, I left them blank, so you can put in whatever labels you need. But I did put in dots, so it's kind of like you've got a grid you can follow. Okay. The one on the left, that's the original graph. So that's like the one that I did in red. And then the one on the right is the new one. The original graph is going to look the same all of the time. Once you graph the original for sine and the original for cosine, that never changes. So as long as you graph the original once for sine and cosine, then you're all set. So there's a sine, cosine, and a cosine, and another cosine. So five questions. Any questions on where to find the homework? This is just online. Yeah, so you can print it, or if you need a printed copy, I can print it, or you can do it just on a separate piece of paper, or you can do it in like Cami and just show me your Chromebook, whichever way you want to do it.
Can you print it?
Sure.